Namaste, my friend, and welcome to JEE Physics with Typical Monk. This is class 4, and today we meet the law that runs every single problem you will ever solve in mechanics. Nothing moves and nothing stops without a force behind it. Newton gave us 3 laws, simple to state and endless to apply, and today we add the one force that decides whether anything slides at all: friction. When Sarah pushed a box across the floor in a JEE problem for the first time, she wrote force equals mass times acceleration and stopped. But she forgot that the floor pushes back too, with a force that has its own personality, its own limit, and its own direction rule. Every connected block, every incline, every banked road you will ever see in this exam is really just Newton's second law, applied one body at a time. Take a slow breath. Let us begin. So what will today's class give you? First, Newton's 3 laws and how to draw a clean free body diagram for any single body. Second, pseudo force, the fictitious force we add only inside an accelerating non-inertial frame. Third, connected bodies, pulleys, strings, and contact forces, and the constraint that ties their accelerations together. Fourth, friction, static, and kinetic, and the angle of repose that tells you exactly when a block starts to slide. And fifth, banking of roads and motion on a rough incline, where all of today's ideas meet in one JEE-style problem. Ready? One idea at a time. Let's start with the 3 laws everything else in mechanics is built from. Newton's first law: a body stays at rest or keeps moving in a straight line at constant speed unless a net external force acts on it. That resistance to change is inertia. Newton's second law: force equals mass times acceleration, applied component by component, and it holds only in an inertial frame, one that is not itself accelerating. Newton's third law: every force has an equal and opposite partner, acting at the same instant, but on the other body, never on the same body. The free body diagram: isolate one body, draw every external force acting on it, weight, normal, tension, friction, and nothing else, then write force equals mass times acceleration. Watch how a single free body diagram, drawn correctly, solves the whole incline problem before you write a single equation. The weight, mg, always points straight down, but on an incline, split it into 2 components along the tilted axis: mg sine theta down the slope and mg cosine theta into the surface. The normal reaction, N, only ever balances the component of weight pressing into the surface. So N equals mg cosine theta, never the full weight. Friction acts along the surface, opposing the tendency of relative sliding. Here, the block tends to slide down, so friction points up the slope. The block is exactly on the verge of sliding when mg sine theta equals the maximum friction, mu times n, and that borderline angle is called the angle of repose. David used to draw friction pointing wherever the applied force pointed. The day he learned to ask which way the surface tends to slide, his incline problems stopped costing him marks. 3 more ideas that turn up in almost every JEE mechanics question. Static friction is not a fixed number. It adjusts itself from 0 up to a maximum of mu s times n, exactly enough to prevent sliding. Kinetic friction, once sliding starts, settles at mu k times n and stays roughly constant. The angle of repose is the incline angle at which a block just begins to slide under gravity alone, and it satisfies tan theta equals mu s, the same number as the coefficient of static friction. Pseudo force appears only inside a non-inertial, accelerating frame. Its magnitude is mass times the frame's acceleration, and it always points opposite to that acceleration. Banking a road lets a car take a curve at its design speed with 0 help from friction when tan theta equals v squared over rg. Friction only widens the safe range above and below that speed. Lisa once tried to add a pseudo force while standing on the ground, watching a lift accelerate past her. But the pseudo force belongs inside the lift's frame, not hers. Time to solve a full JEE numerical together. Slowly, the monk's way. A block of mass 4 kilograms sits on a rough horizontal table, coefficient of friction 0.2, connected by a string over a frictionless pulley at the table's edge to a hanging block of mass 2 kilograms. Take g as 10 meters per second squared. Find the acceleration of the system and the tension in the string. Step 1. Given mass 1 is 4 kilograms on the rough table, coefficient of friction 0.2, mass 2 is 2 kilograms, hanging, g is 10 meters per second squared. Step 2. The free body diagram of block 1. The string pulls it toward the pulley with tension T, and friction F resists that motion. So T minus F equals M1 times A, where F equals mu times M1 times G. Step 3. The free body diagram of block 2. Tension T pulls up, weight M2G pulls down, so M2G minus T equals M2 times A. Step 4. Combine, add the two equations, so tension cancels, M2G minus E times mu times E, 1 times E equals M1 plus M2, all times A. Substituting, 10 times 2 minus 0.2 times 4 over 6 gives it equals 2 meters per second squared. Step 5. The answer. Tension comes from either equation. T equals M2 times G minus A, that is 2 times 10 minus 2, which is 16 newtons. So the system accelerates at 2 meters per second squared with a tension of 16 newtons. Let's see that same setup as one clean picture. Two bodies, one string, one shared acceleration. Isolate block 1 on the table. Its forces are weight M1G down, normal N1 up, tension T toward the pulley, and friction F opposing its motion. Isolate block 2, hanging. Its only forces are weight M2 down and tension T up, the very same T, because the string and the pulley are both ideal. The string is inextensible, so both blocks are forced to move through the same distance in the same time. The accelerations must have the same magnitude, which we call A. Right force equals mass times acceleration for each block on its own. Then add the two equations together. Tension cancels and a single equation gives you A and then T. John once tried solving this by writing one giant equation for both blocks together, tension and all. The moment he isolated each block separately, the algebra stopped fighting him. Now sit up straight. These 5 lines are exactly what JEE tests, question after question. 1. A free body diagram shows only the external forces on the one body you isolated. An action and its reaction never appear on the same body. 2. For an ideal string over an ideal pulley, the tension stays the same throughout, and the two connected bodies share the same magnitude of acceleration. 2 separate facts, not one. 3. Friction opposes the tendency of relative sliding between the two surfaces, not necessarily the direction of the applied force. Always ask which way the surface tends to slip. 4. Static friction is not always at its maximum value. Use mu s times n only when the block is right on the verge of sliding. 5. Pseudo force belongs only inside a non-inertial accelerating frame, never added when you are analyzing motion from the ground. Let us drill the G way. Remember the 4 options. Option A, both statements true, and the reason explains the assertion. Option B, both true, but the reason does not explain the assertion. Option C, assertion true, reason false. Option D, assertion false, reason true. First one, assertion. For an ideal string over an ideal pulley, the tension is the same on both sides. Reason, an ideal string is massless and inextensible, and an ideal pulley is massless and frictionless, so no force is used up accelerating them. Think like SATA. Check each statement, then the connection. Is the assertion true? Yes. Is the reason true? Yes. Does the reason explain the assertion? Completely. With no mass of its own to accelerate, the string simply transmits the tension unchanged. Both true. Reason explains. Option A. Second one, assertion. 2 blocks connected by a string over an ideal pulley always have the same magnitude of acceleration. Reason, the tension in the connecting string is the same throughout its length. Both statements are true. But pause, does the reason explain the assertion? No. The equal acceleration comes from the string's fixed length, forcing both blocks to move the same distance in the same time. The uniform tension is a separate consequence of the string and pulley being ideal, not the cause of the equal acceleration. Both true, but the reason does not explain. Option B. Third one, assertion. A passenger in a car that accelerates forward feels a pseudo force acting in the same forward direction. Reason. A pseudo force is fictitious, equal in magnitude to mass times the frame's acceleration, and directed opposite to that acceleration. Check the reason first. That definition is exactly right, true. Now, the assertion, the pseudo force must point opposite to the car's acceleration, backward, not forward, so the assertion is false. Assertion false, reason true, option D. A quick match now. Say each relation aloud before I reveal it. Maximum static friction, mu s times n. Kinetic friction, mi k times n. Angle of repose, tan theta equals mu s. Ideal banking angle, tan theta equals v squared over rg. If all four came to you before the reveal, today's ideas are becoming yours. Here's a favorite G format. I will read some statements. You silently count how many are correct. Statement 1. Friction on a moving object always acts opposite to that object's own direction of motion. Hold your verdict. Statement 2. For an ideal pulley, the tensions on its two sides are equal, only if the pulley is also massless. Think about what ideal really requires. Statement 3. For the same pair of surfaces, the angle of repose is always greater than the angle of friction. Think about where each angle comes from. So, how many are correct? Just one. Statement 2. A pulley must be both massless and frictionless for the tension to stay equal on both sides. Frictionless alone is not enough. Statement 1 false. Because friction opposes relative sliding between surfaces, not the object's own motion. Think of the friction under a walking foot, which pushes forward in the same direction as the motion. Statement 3 false too, because the angle of repose and the angle of friction are the same angle, tan theta equals mu s, just discovered two different ways. One correct, and the other two are traps. Myth 1. Static friction always equals mu s times n. Truth. Static friction adjusts itself from 0 up to a maximum of mu times n. It equals only whatever is needed to prevent sliding and vanishes completely if there is no tendency to slide at all. Myth 2. A pseudo force can be added to a free body diagram in any frame, including the ground frame. True. A pseudo force belongs only inside a non-inertial, accelerating frame. In an inertial frame, force equals mass times acceleration already holds, with nothing extra to add. Time to test yourself. Rapid fire, and every answer today is a number. Here's the rule. I ask, you answer in your head before the reveal. Question 1. 2 blocks, 3 kilograms and 2 kilograms hang on either side of a frictionless pulley. Taking G as 10, find the acceleration of the system. Answer, mass 1 minus mass 2 times G over the sum of the masses, 3 minus 2 times 10 over 5, 2 meters per second squared. Question 2. A 5 kilogram block rests on a rough surface with mu s equal to 0.4 and G equal to 10. What is the maximum force of static friction? Answer, mu s times n, 0.4 times 5 times 10, 20 newtons. Question 3. A surface has a coefficient of static friction of 0.577, close to 1 over root 3. What is its angle of repose? Answer, tan theta equals mu, so theta is 30 degrees. Question 4. A curve of radius 100 meters is banked for an ideal speed of 20 meters per second with G equal to 10. Find tan theta. Answer, v squared over rg, 400 over 1000, 0.4. And question 5. The thinker. A lift accelerates upward at 2 meters per second squared, carrying a person of mass 60 kilograms with G equal to 10. Find the person's apparent weight. Answer, mass times G plus A, 60 times 12, 720 newtons. If you quote that one, today's class is truly yours. Newton's 3 laws, inertia, force equals mass times acceleration in an inertial frame, and equal and opposite action-reaction pairs that always act on two different bodies. A free body diagram isolates one body and draws only the external forces acting on it: weight, normal, tension, friction. Friction. Static adjusts up to μs times n. Kinetic settles at μs r times n. And the angle of repose satisfies tan theta equals μs. Connected bodies. An inextensible string forces equal accelerations, and an ideal string over an ideal pulley keeps the tension the same throughout. Pseudo force lives only inside a non-inertial flame, with magnitude ma, opposite to that flame's acceleration, and Bankin uses the very same idea. Tan theta equals v squared over rg. And next class, we move to work, energy, and power. Work done by a force that changes with position. Found through integration, the work energy theorem, and potential energy read straight off a u of x curve. Do not miss it. And so, my friend, we have put the whole foundation of mechanics together. Force, friction, and the constraint that ties blocks to one another. Sarah, David, Lisa, and John all start exactly where you are right now with this one class. Be patient with yourself. Tonight, revise the friction rules once, slowly. Static adjust, kinetic stays constant, and the angle of repose ties them both together. One idea at a time, you will crack G. Of this I am certain. If this class brought you clarity, subscribe to the channel so the next one finds you. Until then, keep going. I will see you in energy.